Okay. Okay, hello everyone. I'm going to wait just a minute to see if any more join on Zoom. All right, Friday will be Zoom for everyone. Monday is a holiday. Okay, so I'm going to open up the PowerPoint. Okay, can everyone hear me on Zoom? Can you hear me on Zoom?
Yeah, we can.
Okay, thanks. All right. Okay, let me go back. I'm going to share my screen. All right, so we've been looking at alkanes and cycloalkanes. Okay, and some of the things we looked at were the naming. These are the straight chain alkanes. As the number of carbons goes up, the number of possible constitutional isomers increases significantly. And that's a reason for needing to have a systematic way of naming organic compounds, such as alkanes. Right, these are the substituent prefixes. The longest chain is called the parent, or the main chain, and then branches off the main chain are substituents. Okay, and then make sure that you know and be able to identify all of these substituents. Okay, a parent compound will end in ANE, but a substituent will end in YL. Okay, so something like this is 2-methyl propane, not 2-methane propane. Okay, we locate substituents by position number, and we want to give the substituents the lowest combination of numbers. We list substituents alphabetically. So in this case, ethyl comes before methyl. And if a substituent occurs more than once, okay, such as in this example, this is 2,2-dimethyl-hexane, 4-ethyl 2,2-dimethyl-hexane. We use a multiplier prefix for 2 methyls, and then every substituent gets a number, even the same substituent on the same carbon. Okay, this I'll go ahead and go over this again. This is important not only for alkanes, but for just about all of our functional groups, and that is classification of carbons. Okay, and carbons are classified according to how many carbons are directly bonded to them. Okay, so this one on the end here is a primary carbon, and then the second one here is a, or I guess carbon number 4 is a tertiary carbon, directly bonded to 3 other carbons. And then this hydrogen is called a tertiary hydrogen. Okay, and then these 3 H's are primary hydrogens. Okay, this is a secondary carbon directly bonded to 2 other carbons, and then this is a quaternary carbon. Okay, with other functional groups, recognizing the classification will, in some cases, allow us to predict how a particular compound will react, and in other cases, a primary may react similarly to a secondary, but the rates will be different. Okay, we went over straight chain alkanes quite a bit last time. Okay, and then last week we did introduce cycloalkanes, so I'm going to go over cycloalkanes in more detail. Pentane and cyclopentane, for example, are not isomers. Okay, so let me draw those both on the board. Make sure that I'm on screen here. Okay, here is pentane. Here is cyclopentane. Okay, these are not constitutional isomers. Okay, constitutional isomers have to have the same what? Carbons and hydrogens. Okay, and they don't. This is C5H12, and this is C5H10. Okay, so they're not isomers. They have different formulas, and we actually had to remove a hydrogen from each end in order to form that ring. Okay, erasers over here. Right, the smallest possible cycloalkane is this one, and it is called cyclopropane. Okay, as opposed to propane. Okay, when you're naming compounds, make sure that you include or exclude the prefix cyclo when it's appropriate. It's a common mistake to include that I've seen. It's a common mistake to include the prefix cyclo on something that's not cyclic. Okay, so cyclopropane is the smallest cycloalkane. Okay, this one would be cyclobutane. Okay, 4-membered ring. Right, I just had cyclopentane up. Okay, then cyclohexane. Okay, you might see that written as a hexagon, or we're going to talk about in a moment. Okay, you might see it written like this, and we'll explain why that is. These are both cyclohexane. Okay, as far as substituted cycloalkanes, if we have just one substituent, we don't need a number to locate it. Okay, so isopropyl cyclopentane, it doesn't matter where I put that, whether I put the isopropyl at the top or over here on the left or on the right. It's an unambiguous name. All 5 positions on the ring are equivalent. Not so with pentane. Okay, you would have to locate substituents on pentane, the open chain. Okay, and then we alphabetize and we give the substituents the lowest set of numbers. Okay, so butyl comes before methyl. Okay, so that's listed first. This is a tert-butyl group, kind of looks like a T. And then we have a methyl group on 4. 1 tert-butyl, 4-methyl cyclohexane. Okay, this is an isobutyl group. Okay, here's tert-butyl, and instead of connecting to the middle carbon, we connect to one of the carbons on the end. For isobutyl, that is alphabetized under the I's. So it's 1 isobutyl, 2-methyl cyclohexane. And then here's 1 ethyl, 1 methyl cyclopropane. Okay, and these both need numbers, even though they're on the same carbon. Okay, 1 ethyl, 1 methyl. Every substituent gets a number. Okay. Okay, I won't say too much about this because we will look at these in more detail as we come to them. Different functional groups will have different suffixes. Okay, so we take the name of an alkane, we drop the E, and then we add the suffix. And we'll come to those as we consider each functional group. Okay, just as an example, all indicates an alcohol. Okay, so if we have ethane, that's the alkane. We replace one of the hydrogens with an OH, then we have ethanol. Okay, I'm going to skip over this because we'll come to each one of those in the corresponding chapter. Let me go ahead and review conformations again. Conformations are the result of free rotations that take place about carbon-carbon single bonds. Okay, here I have ethane, and as the model accurately shows, we have free rotation about this bond. Okay, and when the front and back hydrogens are as far apart as they can get, that's called staggered. Okay, and that's the lowest energy conformation. Okay, when they're all lined up like this, okay, what's that called? Eclipsed, right. This is the highest energy. Okay, you have what is called torsional strain, okay, in which, okay, I don't have hydrogen shown here, but if I had hydrogens, actually, let's get a couple of hydrogens. Okay, so here, these represent hydrogens. Okay, these hydrogens repel each other in the eclipse conformation, and so the tension along that bond is called torsional strain. okay, which results from eclipsing. The energy differences between staggered and eclipsed are so small that you can't isolate a particular conformation at room temperature. Okay, you have continuous free rotation that's taking place. Okay, this is the Newman projection. Okay, we sight along this carbon-carbon bond. The carbon in front has the bond starting from the center of the circle. The carbon in back has the bond starting from the outside of the circle. Okay, so what is shown is the staggered. And then this is the Newman projection for the eclipsed. And then for a longer alkane, the lowest energy conformation has everything fully staggered. Okay, although you still do have free rotation about each one of those bonds. Okay, and we said that was called torsional strain. The difference in energy between staggered and eclipsed is approximately 12.6 kJ per mole. This energy barrier can be easily overcome just by thermal energy at room temperature. Okay, let's see, we did not cover cyclohexane yet. Okay, cyclopentane. Okay, it's a 5-membered ring. I'm going to go ahead and make a model of cyclopentane. Okay, I need one more carbon here. There we go. Okay, so cyclopentane. Okay, this is not too difficult to build. There's not much angle strain. And by angle strain, what I'm talking about is deviation from the ideal bond angles. Okay, so a tetrahedral carbon has 109.5 degree bond angles. Okay, in a regular pentagon, bond angles are 108 degrees, okay, which is pretty close to 109.5. But there's nothing that says that all 5 of these carbons have to be in the same plane. Okay, there's not a lot of angle strain, but there is, okay, what kind of strain is this when these hydrogens are eclipsed? Torsional. Okay, so there's some torsional strain going on here. Okay, so to relieve the torsional strain, okay, the ring bends so that one of the carbons is out of the plane. Okay, the other 4 are in the plane, but one is either above or below. Okay, and this folding takes place easily at room temperature. This is the planar conformation. This is what's called the envelope conformation. Okay, this is the flap on the envelope. Okay, and then if we look along one of the bonds here, we can see that we have relieved the eclipsing. Okay, the hydrogens are no longer eclipsed in the envelope form. Okay, so that helps to relieve the torsional strain. Okay, let's go to cyclohexane next. Okay, 5- and 6-membered rings are extremely common in natural products. Okay, and while Well, you have a little bit of torsional strain and very little bond angle strain in cyclopentane. In cyclohexane, the 6-membered ring, it's actually very unfavorable to have all 6 carbons in the same plane. Okay, and I think you can readily see when I try to force all of these into the same plane. For a regular hexagon, okay, here we have a considerable deviation from the ideal of 109.5. Okay, in a planar regular hexagon, the bond angles are 120 degrees. Okay, but again, as the model depicts, there's nothing that requires that all of these be in the same plane. Okay, the ring is capable of folding, and the most stable conformation is this one. Okay, and this one, okay, the 4 carbons here in the middle are in the same plane. One is below and one is above. And this is called the chair. Okay, here's the seat, here's the back, here's the footrest on the chair. Okay, to draw a chair, you can start by drawing 2 parallel lines that are offset, like this. Okay, so that's my cyclohexane chair. Okay, you have continuous conversion of one chair to another at room temperature. And in the chair conformation, okay, we can see that there's no eclipsing of the hydrogens. If we sight along this bond, none of the hydrogens are eclipsed. Okay, then we have another conformation, and this is called the boat. I'll draw that over here. Okay, this is the boat conformation. Okay, in the boat conformation, 2 carbons are above the plane of the ring. Okay, this is less stable than the chair. These hydrogens right here, up at the top, these are called flagpole hydrogens. Okay, if you imagine the boat, okay, you've got a flag here at the bow and one at the stern. Okay, so this is less stable than a chair by about 27 kJs per mole. There is torsional strain. Okay, if you look along these bonds, you can see that the hydrogens are eclipsed. There is also some what's called steric strain. The flagpole hydrogens undergo repulsion with each other. Okay, here is cholestanol, a close relative of cholesterol. And The most stable conformation would be to have all of these as chairs, all these cyclohexane rings as chairs. Okay, so there's two equivalent chair conformations. And these two forms interconvert back and forth continuously. Okay, then I want to introduce the terms axial and equatorial. Okay, so here is my cyclohexane chair. And you have two hydrogens on each carbon. And each carbon contains what's called an axial and an equatorial hydrogen in the chair position. Okay, you can start anywhere. Arbitrarily, I start here at the bottom corner, and we alternate. Okay, so this one goes straight down. The next one goes straight up, and straight down, then straight up, then straight down, and then straight up. Okay, so these are axial. These are what are called the axial hydrogens. Okay, the other hydrogens are the equatorial. And okay, the equatorial hydrogens, again, I'll start at this bottom right corner. Again, you can start anywhere. Okay, if you think of a globe, the globe spins on its axis, and then that horizontal line is called the equator, and so the equatorial are more horizontal. To draw the equatorial, okay, starting here, okay, I want this one to be parallel, not to the first bond, but to the second bond over. So these lines need to be parallel. Okay, and then going around this way, okay, this line needs to be parallel to this one. This one parallel to this one and to this one. Okay, and then over here, this is parallel to this line. And then this is parallel to this one. And this is parallel to this one over here. Okay, so those are the equatorial. Okay, when you're drawing the equatorials, the three equatorial groups on the right will point to the right, and three on the left will point to the left. Okay, so it would not be correct to show this one going that way. Okay, so that's how you draw the axial and the equatorial. Okay, when you have the ring flip, okay, those substituents that were axial, okay, let me just mark this with a hydrogen. Okay, so this one is axial. This is one of the chair conformations. Okay, notice what happens when I interconvert. Okay, now it becomes equatorial. Okay, so you have that continuous exchange between axial and equatorial. Okay, here we have methyl cyclohexane. Okay, I can put this anywhere. All right, the methyl interconverts between axial and equatorial. And this is an important point. In general, there's more space in the equatorial position. Okay, so substituents prefer to be equatorial if they can. Okay, so let me put that on there. There we go. Okay, so that's the equatorial methyl, and then the axial methyl. Okay, in the axial methyl, okay, you have some hydrogen-hydrogen repulsion that takes place. These are 1,3 diaxial interactions. If you have a very large constituent, okay, like a tert-butyl group, okay, I'll show you a tert-butyl group, or even an isopropyl group. Okay, here's an isopropyl. One more carbon. There we go. Okay, if you have a very large group like a tert-butyl, this effectively locks the ring. There we go. The tert-butyl really has to be equatorial, and it prevents this equilibration. Okay, the other substituents will fall where they may, but the tert-butyl takes up so much space that it really has to be equatorial. Okay, cis-trans isomers. Okay, there are two situations where we can have cis and trans isomers. These are cyclic compounds and alkenes. Okay, we haven't come to alkenes yet. Okay, cis-trans isomers are also called geometric isomers. They differ from constitutional isomers in that the skeleton is the same, but the three-dimensional shape is different. And cis-trans isomers cannot be interconverted by rotation about single bonds. Okay, so here we have cyclopentane, 5-membered ring. And for 1,2-dimethyl cyclopentane, 1,2-dimethyl cyclopentane, okay, we could have both of those methyls on top, like this. We could have them both on top. Or we could have one on top and one on the bottom, like this. Okay, this is the trans, where they're opposite. And when they're on the same side, okay, that's cis. Okay, and you probably noticed that I had to break a bond and reform it in order to go from cis to trans. Okay, with an alkane, okay, you have different conformations, but they're not, you don't have cis-trans isomers. Okay, so we include the name cis, we include the prefix cis at the beginning. So that's cis-1,2, and then this is trans-1,2. You could also represent these two isomers this way. Okay, there's a hydrogen on each one of these that's omitted for clarity. But the cis has both methyls either going back or both coming forward. The trans has one back and one forward. Okay, these are different compounds. They have different melting points and boiling points and so on. These are called geometric or cis-trans isomers. Okay, so here's cis and trans 1,4-dimethylcyclohexane. Okay, and these are two ways of representing those two isomers. Okay, for trans 1,4-dimethylcyclohexane. Okay, let me go ahead and make a model of that. Okay, too many carbons there. Okay, so here is cyclohexane. Okay, and for the trans, okay, it should be pretty easy to see that that's trans, okay, because this one's on the bottom, this one's on the top, so that's a trans 1,4. Okay, when I do the ring flip, oops. When I do the ring flip, okay, now they're both equatorial, but it's still trans. Okay, because especially if you look at the hydrogens, this one's down, this one's straight up. Okay, so this one's still on the bottom, this one's on top. Okay, so there was no change in cis and trans, but there was a change from axial to equatorial. Okay, so here's that shown on the slide. Okay, this is pretty easy to see on the left that the methyl's on top, and then the other methyl's on the bottom, so that's trans. Then we do the conformational ring flip. Okay, the methyl on the left is, okay, it's the lower one, and then the methyl on the right is the upper one. Okay, so they're opposite, so it's still trans. The conformation where both methyls are equatorial is more stable than where they're both axial. Okay, and for cis, to go from cis to trans, or trans to cis, I guess it is, trans to cis, okay, this time I can't just fold the ring, I actually have to break a bond and reform it in a different place. Okay, so this is cis. Both methyls are on top, one is axial, one is equatorial. Okay, when I do the conformational change, like this, it's still cis. Okay, but the one that was axial is now equatorial. The one that was equatorial is now axial. Okay, so these have equal stability. Okay, one axial, one equatorial is the same as one equatorial, one axial. Okay, so we have about 2 minutes remaining, and Okay, so draw the alternative chair conformations and state which one is more stable. Okay, so these are all cis. So this is 1,2,4 trimethyl. Okay, so this is one way. Okay, I put all three of these on top. These two happen to be axial. This one is equatorial. There is some torsional strain going on here between these hydrogens. Okay, if I do the ring flip, okay, I would say this is even worse as far as torsional strain, because these are now even closer together, where the 1 and 2 are both axial. Okay, I think we're about out of time, so I'm going to go ahead and stop here. Okay, so again, Friday is all Zoom for everyone.